Sure.
Hey, so I'm Santiago Daza, D-A-Z-A. Today I will be the interviewer and I will be interviewing David Hintz over here. So if you'd like to go ahead and introduce yourself as well.
Hi, I'm David Hintz, and I'll be being interviewed for this assignment.
Perfect. So jumping straight into the technical question here. The question that I have for you is going to have to do with trees. So I hope you like trees.
Okay.
And we're going to have you take a binary tree, a binary search tree, and so it's actually not going to be a binary search tree, it's just going to be a binary tree. So it's not going to have the restrictions of a binary search tree. Items on the left side of the node will be able to be greater, and items on the right side will be able to be smaller. So it's a binary tree, but it's not going to be a binary search tree that we're dealing with.
So to clarify, uh, every node will have at most two leaves below it that is pointing to.
Yes, so it'll basically just
Got it.
be an n-ary tree with n equals 2, but they will not be ordered in any particular way.
Okay.
And so what you're going to be given is you're going to be given the root of the binary tree. So it's already going to exist, right? And it's going to be an array-based implementation. So you'll be given the array that corresponds to the tree. And what I would like you to code up is the sum of all of the left leaves. And what is meant by leaves is, of course, any nodes without any children. And what is meant by a left leaf, that would mean that it's the left child of the parent node.
Okay.
So if a node has two children and neither of those children have any further children, the child on the left will be the left node.
Right. I believe you're not sharing your screen on Zoom yet.
Yes. Yes. So that was just the specifications. So I will go ahead and start sharing that. There it
Sure.
is.
So far, I've only just written these notes.
Yeah.
Okay, so
So let's
um,
say, for example, you're given an input tree, which is represented as an array. Oh, well, it's got a little bit of formatting weirdness there. But let's say, oh, it's still being weird. Okay, so there we go. That should be fine. So this tree will be, for instance, represented by 3, 9, 20, 0, 0, 15, 7. So for this is just an example tree, but for any tree that is input into the actual function that you're making, it will return the sum of all of the left leaves.
okay. To clarify on what the left leaves means, I'll just draw something
Yeah,
on
yeah,
Zoom.
yeah. I strongly recommend drawing it out on Zoom.
Sure. So this is our node, whatever value. So I'm assuming everything in a box will count as the left leaf, since the left subtree of the node above it.
That is correct. And you would be
Okay.
returning the sum of all of the left leaves in the tree.
And the leaves would not have any subtrees of their own.
No,
So in this
they
case,
would
this would
all
no longer be a leaf.
that would no longer be a leaf. Yes,
Okay.
it would have to be, so both of its children would have to be null pointer.
Okay. Thank you. Are there any other constraints?
So for the actual array slash tree that you're given, any null pointers will be represented by null. It will only be integers,
Okay.
and they will only be integers from 1 to, it won't be anything excessive. So nothing in the millions or billions, but there's technically not an upper limit to the number, but it should be able to handle
Would
a
would the
reasonable.
sum fit within the size limits of an integer
Yes,
variable?
yes,
Okay.
yes. Whatever you return will fit within the size limit of an integer.
You said that was greater than 0 for
Greater
the
than
nodes,
0, yes. So none of the
not
values will be
equal to
0.
0.
Yes. And the sum will, as a constraint, the sum will be able to be represented as an integer.
Got it.
As a matter of fact, let's constrain it even further. The numbers will only be from 1 to 1,000.
Okay. I'll just represent that as x for the sake of this.
So then you're going to be implementing some sort of traversal that will allow you to get the sum of all the left leaves.
Okay. Is there an example or any mention
Yes.
of what
So
the
so for
actual
ex
node is? Yeah.
yeah, so for example, this tree right here, you would want to return a value of 4, because you would be taking that in this tree, which you sort of drew out earlier, the left children would wind up being 9 and 15. So you would
Okay.
add those two together and you would return an integer value 24.
That makes sense. Is there a given name for what I call when I'm searching for the like, left subtree or right like child node?
So we're just going to be using C++ std for the tree. So the nodes will have a left and the nodes will have a right, and they will have a
Okay.
value associated with them.
So when calling the pointer, I would just say whatever the root is, pointing to left or
Yep.
pointing to right, like this.
Yes, so it would just be root, then pointer, then left or right, and that would be pointing to the left or the right of the node.
Okay. And the only value I'm given then is this array. Is that right?
Yes, yes. So you would be given the array that represents the given tree that you are to traverse. And from that information, you're going to want to find the values that you want to sum together. And you're going to return the sum of all the values that you found.
Okay. So before even thinking about the coding, I'm just going to go ahead and draw this example here in visual format. So 9 doesn't point to anything because both of those are null. 15 and a 7. Okay. Another question, would repeat values, could those show up in these trees?
There would not be any repeat values.
No repeat values. Got it. So, I might either do a depth first or a breadth first search. Both would have same time complexity, so I just want to find the left nodes. I guess I could do it either way. So if I did, I'll start with talking about a breadth first, going just left to right on each level. So first I'd start with my root, happens to be 3 in this case. Then I would move to the left node. I think I see. So left would be 9. Am I allowed to use additional data structures like arrays, vectors, something like that?
Yep, you're able to use any additional data structures that you'd like.
Great. So if I'm doing breadth first, of course, I will have my own queue of nodes over here. So 3, 9, 20, and so on. But additionally, I'm thinking it might be good to have another one for just the left nodes. So 3, the left subtree would be 9. And then done with this level, on to the next one. Sorry. Yeah, 3, add 9 and 20, I go to 9. 9 has null and null, where it's 2. So it represents it with a 0 with a slash through it to show null, shorthand. I'll say I'm not going to add anything to this bottom queue if it's null. Moving on to 20. Left would be 15, so I could add that to the second queue. I think a vector would actually make more sense for this bottom one, since that way I can just iterate through it once I'm done. And then
Makes sense.
15 here. 7 is the right node of 20, but it's the right node, so I'm not going to add it. So once I'm done iterating through the entire array, and of course this is on a queue, so these would all get removed as I go through them. So once the queue is empty, I know I'm done going through the entire array with my search function. now I've saved this vector, I will just, I guess, loop through it and add everything together.
Okay, yeah,
Now,
that approach would ultimately get you the solution, I believe.
well,
Um,
I think I'd have to consider, because if there was another node here,
right,
say four,
you'd have to basically
I'd
um,
have
figure out the logic to figure out that it is a left
a leaf. Yeah.
leaf. Yeah.
Um, something. So when I'm adding 9 to the queue uh, and to this vector, I will actually currently be looking at 3 lefts the value. So if I go 3 dot left, well, I know it's left. I could just check another if statement, check if this 9 right here has any children. If it does have children, then I won't continue with the step of adding it to this vector down here. If it does not have children, then I'll add it here. I think that could work. Um,
Right, and in order
yeah,
to sort of implement these sort of tree traversals, it is generally recommended to at least consider some sort of recursive approach.
okay. Hmm. Well, if I'm doing recursive, I don't know if it would be easier to do a depth first search. Um,
But regardless, any recursive solution can also be done iteratively. So it's whichever you feel more
okay.
comfortable with.
I think I like this better. I've thought through it. I think it's possible to be a recursive solution with that works a bit faster and use up maybe less space. Because I think there's, I'm not sure. So right now this is just n space complexity, I think. Well, plus this vector, but this is going to be so small that it's really not going to be negligible. Not going to be a big issue compared to the size of the tree itself.
Theoretically.
Yeah.
But yeah,
Yeah, most it would
when
be half the size, I'd assume, because you need, I think the most left leaves you could have is something like this. It just goes on and on. So it'd be half the size. So I guess still n complexity. I like this. I think I'm gonna go ahead with it and start coding.
yeah, if you could just go ahead and start sort of writing it down in code form a little bit, I'd
Yeah.
love to see your thought process there.
Okay. So we're gonna be implementing it in this method here, right? And
Yep, yep.
it's all the same sum
I
of left leaves
just
function.
Yep, I just got the sort of skeleton code set up for you here, and you can just
Great.
insert your solution code inside using the tree node root.
Okay. If you don't mind, I just have this curly bracket here. It's easier for me
Feel
when I look at it.
feel free to format it however you feel most comfortable.
Okay. And all my code would fit inside this function. I wouldn't.
Yes, you would be returning because that's where your in the tree itself would be input into this function, and then you would be returning the value from that function.
Okay. If I wanted to, could I initialize variables outside of this?
Yes.
Okay. Um, I don't think it'll be needed for this actually, but it's good to know.
And feel free to define
And
any additional functions that would help with your solution.
and this tree node variable, is this just the array? Can I?
So that's just what's being passed into the function itself. So that's just specifying that this root right here is going to be the address of the first element of the array.
Right.
So that's
Right, that
just
makes sense.
that's just saying that it's the root.
Got it. So starting off,
So from there
I have my roots.
you'd be able to go root left or root right or whichever way.
Okay. So starting off, I guess I'll just make an empty queue. I don't exactly remember the syntax for this, but going off, I'm just going to model it after how I did the stack earlier. And if I'm wrong, then
Feel free to just make it pseudocode as long as we both know what you're doing with the functions.
sure. So queue of tree nodes. I'll just call this search queue. And I will also make a vector of tree nodes. And I'll just call this left leaves. So I'm going to store, while I'm searching, I'm going to store all the nodes in the queue and remove those. And then in the vector, I'm going to put all the left leaves as I come across them. So in by pushing the root value into the queue. Then a while loop that will continue looping as long as this queue is not empty. So while it's not empty, here is where we're going to do the majority of our work. So we're going to have the search function, and I'm going to add to the vector here. So drawing I made. Right, so the roots, I'm going to go left first and add that to the queue. So first of all, I need to check if the value I'm looking at is null.
Now,
So,
just to suggest a base case
yeah,
here, what would happen if you were passed an empty tree?
empty tree is that, so that is not, that's possible within the bounds of this problem.
Yes.
Okay. In that case, this root would be a null pointer.
That's right.
Well, I could add a null pointer to this queue, and then at this step, before I do anything else within this while loop, I'm going to check if this is a null pointer.
Mm-hmm.
And if it is, then we don't look at its children, just pop it. If this is the if the entire queue is just a null pointer, if the entire tree is just a null pointer, it's nothing there, then
Now, if it is a null pointer, it will just evaluate to false if you try to evaluate it.
um, what do you mean if I try to evaluate it? Just gonna get some
So
clarification.
yeah, so if you were to have some sort of if statement or Boolean check, like if true, if false, if that pointer is pointing to a null pointer, it will just evaluate to false.
Right.
And in that case, we'd like it to return just 0.
So that's if it's an empty. Okay.
Yes.
So I'm going to make, first of all, an integer turn sum to equal to 0. So if we do get an empty queue or an empty tree, we won't add anything to the sum value. It'll just be 0, and then that'll be the default we return. I think that makes sense. So if it is an empty tree, this root will be a null pointer.
Yes, and if you try to evaluate it with like an if else, it will evaluate to false.
Right.
So for example, if you were just to feed it into an if statement, if just parentheses and then root, that would just evaluate to false.
I see. That works. I think what I have here, this if statement should be able to handle that too, I think. If I have everything else tied to whether or not. Let me see, I'm gonna write this out. Once I have it on the page, should be easier, I think, for me to think about it. So if this is null pointer, we aren't gonna do anything. So drawing here. If the first node is null pointer, we don't do anything. We leave, return 0. If this is a value, whatever. This is whatever, it's null. This is another value, n. So what I'm going to do is have x, add null, add n, go to the next value, and remove x from the queue. This is null, we're going to do nothing, and just go to the next value and pop this null off the page. And then n, it will be, sorry, n will not be a null pointer. So then whatever is inside this if statements here will be actually done. That's what will continue with the children of this n. I think that's what we're going to do.
Okay.
So we're going to add to the queue the 2 children of the current node. So let's push and then peek at the current value left. So add that. Now I'm going to do an if statement to see if this left subtree, if it exists and has any children. So I think I'll need to actually check if this is a null pointer as well. Before I check if it has before I check if it's a leaf. Because I
Okay.
could be, because at this stage, I could be just putting a null pointer into the queue. I need to see if it's able to have leaves first. Just fast search, copy and paste. Not equal to null pointer. I will null pointer. I will check its children. So if the left is child of the last one is equal to null pointer and the right child. So if we're checking if the next one has no children, let's just copy that. Whatever, this is part of the same line.
Gotcha.
So in this case, we know that has no children. So we can add the node that we're looking at to the vector.
Yep. Because you know that's going to be a left leaf.
Yeah, I believe dot push will work.
Yep.
Cool.
Or in queue or whichever.
Well, this is for the vector. So
For the vector, yes. Vector is push underscore back.
Push back. Okay. Great. So that's just checking the left subtree of the current node in the queue. Let's do the same thing for the right. And this formatting got messed up. Hold on. No, I don't have to do that because do I? No, I do.
Yeah, and feel free to write out the process as you're coding
Yeah.
it to draw out the process as you're writing it down.
Yeah, no, that's incorrect. I don't need to do that because what I have so far is I checked the left node for any children. That was writing to check the right node, but we don't have to do that because any right node will not be a left leaf. So we can just ignore that step. And
But what if, for example, you go to the node on the root to the right, and then
yeah,
that child has a left child? So if n has a left child,
yeah.
that would also be considered a left leaf.
Well, what I have so far, draw it out, I have, so as long as the queue here is not empty, then I'm going to look at the current node. If it's not null pointer, then it's a node. And now I'm going to check left child. Does this have, is the left child, yeah, just looking at the left child and adding the left child to the queue here, which is what we're using to keep track of just all the nodes in the tree. I'll need to do that for the right node as well, but I don't need to do this whole statement here because this is checking if the left root of this child is a null pointer, and also checking the right root of this child, because we're still on this first x. So this all here just verifies that that the left node is a leaf. Then after this, I'm going to do another push for the right node of this x.
Okay.
But I'm not going to implement this stuff here again, because we know that this n here isn't going to be a right node or a right leaf, but it'll still be in the queue.
Okay.
So once we get to here, then we check this one's children for leaves and so on.
Yep. Perfect.
That's the general structure.
Because if it's going to be on the right, then it's not going to be a left leaf. You're right.
Right. So done with this if statements, I will push the right node of the root to here, and then we'll be good. Now, I think this is pretty good for now. I am noticing an issue I didn't think of before, which is I'll need a way to know when I've reached the end of the queue, so I'm not just putting in. Oh no, hold on. I'm mistaken. I need a way to know not to add extra null pointers if the one I'm already on is a null pointer. But I've already handled that. So let's see, now that this is all done, I'm gonna just talk through it. So while it's not empty, we're gonna check if it's a null pointer. If it's a null pointer, just move on to the next value in the queue. It's not a null pointer. Add the left child, check if the left child is a leaf, add the right child. Great. What I'm missing in the while loop is I still have to pop whatever value I'm looking at.
Yep. I was just about to suggest that.
And I think that should work because that'll just get the front value. And then, yeah. I guess the front value reduces it. And that should get the edge case of the empty tree, which will just have the null pointer. This is a null pointer, so we ignore all this, we remove it, and now the queue is empty, we're done with the loop. Great. Now, what we have to do is loop through our vector. And we've already verified that all the things in the vector are left leaves. So we can just add everything up and then we should be good. So 0 is less than size minus 1. Plus so this return sum integer, we'll just add.
And right now it's a vector of nodes. So you would want to access the value at the node.
Right. So just thinking, so you can access it just with the index. So I believe if I just do the index, should be I dot value, but
And
with an
then,
arrow because it's a node.
yep.
I think that should be it. We add that, iterate through that, size minus 1, so shouldn't be out of bounds. I that might be it.
Could you explain why you're iterating through left leaves dot size -1?
Yeah, so let's say we have the vector here. I'm going to draw it. Going off the example gave me 3, 9, 20. So we have 3. We'll iterate through. 9 gets added here because it's a left leaf. The other left leaf that gets added is 15. So now the size of this vector would be 2, but we can't go to index 2. We have to go to index 0 and index 1. So that's why I'm doing size -1 as the upper bound. Or, yeah, because that less than would be the last value it goes to is size -1. So it iterates twice, I believe.
I believe it should be 0 indexed.
I'm sorry?
Yeah, I believe it should be zero indexed, so it should be fine.
Okay. Yeah, so I should just loop. In this case, it should loop twice, once for 0, once for 1. And I think that's it.
But I believe the -1 shouldn't be necessary because it won't go through for the 2. So if you just have it without the -1, it'll go through index 0, then it'll go to index 1, and then it won't try to access index 2 because it will already have met the for loop condition. So I think it should be fine just without the -1.
Well, I thought it adds. Yeah, I'll go with what you said.
Yeah,
fine.
I think it should be fine. But yeah, I mean, the code looks good. If you could just walk me through an example with a few values in an array, I think it should be
Sure.
good to go.
Sure, I will. Quick, I don't know if I have a selection tool. There we go. So,
So
drawing it out here, let's say I have the array 4, 7, 18, 19, null. Oh, let's do a big example here. 20, 3, and 5. I think that's right. I'll draw it out because I'm not sure if not sure if the nulls are in the right spot, but 10, 15. This is empty. This is nothing. It's 20, 3, 5. For this, wouldn't, I guess that'd be fine. There would be an extra bunch of nulls here, but they won't even really do anything for the program. Extra nulls at the end of the array, I mean.
So
So
let's say for the purposes of this example, there's another value on the left of 20. So don't worry about putting it in
sure.
the array, but just go ahead and insert it into the tree.
And 8 here. Yeah, that works. Yeah, I realized I'd only had 1 left there.
So just go ahead and walk through the how your code would tackle this problem.
Of course. So we start with roots, which will point to the 4. Do you mind scrolling up a bit on your end just so I can have them on the same screen? Thanks.
There you go.
So we start with the roots, which is 4. That's what we're given. We make a queue, which I will draw here. And the vector of left leaves, which I'll just have here, plus a value equal to 0. This is the return sum integer that starts off as 0. So search Q, or Q, we're going to push in the roots, which is 4. Next, we go to this while loop. So while the search Q is not empty, which right now it's not, it has this 4. We're going to go to the next line. If this value is not a null pointer, so it's not a null pointer, we can go ahead. We're going to look at the left, which is a 7. And we're going to push that into this queue. Now, next line, is this a null pointer? No, so we can go ahead with this after this if statement. So now, starting at 4, go left again. Is this a null pointer? No, it's not. So we know that this next line here is not going to get executed because this is not equal to null pointer.
Right.
So now we're done with this if statement and with this one. Now we're going to push in the right value. Starting from the root, go right. This goes into the queue. And then we pop 4. We're done. Now we're going to go to 7. We're going to start here at 7. Do the same thing. Not a null pointer, so we go on. Left is a 19. We add that to the queue. Does left of 7, 19, does left of that equal null pointer? No, it does not. So again, this does not get executed. Go back. Now we add the right, which in this case would be null. I'm just going to write an N if that's okay.
Yep.
And then pop. Now we're on 18. Do the same thing, not a null pointer. Keep going. Left, we add a null. And because this left is a null pointer, we are not going to execute this part here. And then we just add right, which is 20. Pop this, 19. Left is 3. We'll add it. This is 3 is not a null pointer. And it also does not have any children. Both left and right of 3 are null pointers. So this does get executed. We will add this 3 here to the vector. And then add 5. This is the right subtree of 19. Pop that. And this is null. Say if this is null. If it does equal to null, we are not going to execute this, and we're just going to pop it from the queue.
Yep.
Same thing here. This is a null. We're going to pop it. Now we are looking at this 20 here. Left is 8. We add it here. Right is, or left is not null, and both of its children would be null. So again, we add this here. And right of 20 is null again. Pop that. 3. So now we're back here. Left is null. We'll add it. But we're not going to execute this because the left is null. We add the right again. It's another null. Pop 3, 5, same thing, another 2 null pointers. 8. Now we're fine on 8. Its children are again 2 null pointers. Now all the rest of these are null pointers. So as soon as we get to this part of the while loop at the beginning, we're gonna know we don't execute this, we just pop them. So these are all gone now.
Yep.
Now we're done with the while loop. Last thing we have here is this loop. So for ints I equals 0, we're going to iterate through the vector and add these values to the return sum int. So start with 3. 0 plus 3 was 3. That's loop 1. Loop 2, now we're looking at this 8. So 3 plus 8 is now our 11. So return would be 11 at the very end of the function.
And that would get you the answer for that example. And
Right.
yeah, I think that bit of code right there would generally be able to tackle this problem right here. And yeah, good job. You did a good job sort of illustrating how it would go through in an actual scenario. And yeah, I think that would do the trick.
Great.
Um, moving on to the feedback portion. I'll try to keep it a little brief. I'm not sure how much time we have left. But yeah,
I think
no,
it was a little longer, but
no, it was good. But yeah, no, you did a really good job walking through the actual your actual thought process. You were able to sort of draw out the whole sort of structure and think about the whole solution before actually starting to implement any of your code. So that was quite good. And I think you sort of got a good base idea with the queue traversal and the two data structures that you were using to solve the problem. And yeah, I think you implemented that in a very straightforward but very good way, starting off of those initial ideas. And yeah, I think you did a good job of saying your thought process out loud as you were going as well.
great. I could
And
ask a question. I don't know if that's,
yeah, of course.
was there a faster solution I could have done in
Um,
terms of time capacity?
so in terms of time complexity and in terms of code complexity, um, when it comes to this sort of tree traversal, usually the absolute most optimal solution will be done through recursion. So that's sort of one of the solutions that you could go with for this type of problem. But like I said, any recursive solution can also be done iteratively. So this is basically just the iterative approach of the recursive solution. And when it comes to the actual recursive solution, it's basically just like two lines that take care of all that stuff without the additional data structures.
Okay, that makes sense.
So yeah, there is a more straightforward sort of recursive solution. Um, but you know, recursive solutions are kind of mean, just in the sense that they're not the most straightforward to sort of think through and work through.
Right.
So an iterative solution works perfectly fine. It should be fairly efficient. Maybe not O of n, but it won't be incredibly inefficient either. Um, like there are
You know, I
some.
think it would be worst case would be 2n. So that's still O of n. You
Just let
take
me
off the
see here.
constant.
So yeah, you would have to at worst go through the tree, and then yeah, there's nothing nested, so it would still be O of n.
Okay, great.
Um, yeah, yeah. So in terms of order, that is about as good as you can get it. Um, it's just in the sort of the space complexity can be made more efficient by not using the additional data structures, but in terms of time complexity, O of n is the best you can get.
Okay.
But
All
yeah,
right, that's good.
but yeah, besides it not being recursive, it's a good solution. It's a good iterative solution, and I think you did a good job illustrating your thought process. And and yeah, I think you asked good questions when it came to sort of getting more more details or thinking about edge cases. And yeah, overall, yeah, that was a good job. The solution looks good. Looks like it should work. It's not incredible. It's not inefficient, and it definitely gets the job done. And it returns what it's supposed to return.
All right, great.
But yeah, good job. That was that was very good. And if you're able to whip that out during a technical interview, I think the interviewer will be quite pleased.
It's good to hear. All right, thank you. I think we should be good now. Yeah.
So I'm going to stop the recording. Well, first I'm going to stop sharing, and then